Namaste, everyone. Welcome to the session 6 of the programming bootcamp. I hope that you had time to look at the past exercises. And today we are going to continue with simulated annealing. Last week we discussed simulated annealing, and that was an introduction to optimization problems. Let me share my screen quickly. Right, so this week we are going to continue with simulated annealing first, and then we will move on to some other optimization problem, traveling salesman problem. And then we will discuss some data processing techniques, examples, gradient descent, and finally linear regression, hopefully in the next hour. Okay, so continuing with simulated annealing. What is simulated annealing used for? It is a stochastic optimization process that can be used for optimizing problems where you have gradients, but you necessarily do not need gradients to optimize the function. And for problems where you do not have gradients, such as the traveling salesman problem. Okay, so that's an example of a problem where you do not have gradients. So that's where simulated annealing will be more useful. Okay, so last week what did we do? We did discuss a very simple example of we discussed a simple example of what an objective function is, and in the literature it is also called a fitness function, and in the literature for simulated annealing it is called energy function as well. And basically this can be any function. It could be single dimension, as in this case, or multiple dimensions. That could be where you can specify the dimensions of the function. It could be 10, 20, or 100. And equivalent to that thinking is like you have like a traveling salesman problem with 10 cities, for example. So that's a multi-dimensional problem. So your dimension is 10. So similarly, the function here is could be having such dimensions, right? The other thing is the range. So we want the function to be limited within a range when you are searching for the optimal solution. That means optimal values of x, right? And for example, whatever values we guess. So in a way, simulated annealing is an efficient way of guessing solutions, right? It's just not guessing, but efficient way of guessing solutions. So we can be guessing solutions. We could put any values here over time. And so firstly, our guess should be limited between the range of -5 to 5. So you should always have a if statement to know if that's a valid guess. Okay, so this is not a valid guess. Why? It's because it's not, it goes beyond our limit, and that's the range that we want it to be, for example. Okay, so a valid guess would be 4.9, for example, in here, and that would be fine. Or -5, let's say it's including the 5, -5 and 5 in the range between them, right? So that's a valid guess. And basically whatever you have guessed, either single dimension or multi-dimension, you can give it to your objective function. This is your objective function, and the objective function will evaluate it and tell you what is the fitness, or what is the fitness, or how good is your guess. And the goal is that over time you are going to reduce in an optimization problem as such. Here there can be different sorts of optimization problems. Okay, this is a minimization function. That means the fitness function, the objective function or the energy function should have a minimal value. The lower the value, the better. Okay. And um, in other problems, there could be a maximization function where you want to find what values in your decision variables, these are also called decision variables, will give a maximum value of the energy or the fitness function, right? And for example, the traveling salesman problem is kind of a minimization function as well, because you want a route, go through a route that gives the minimal distance, right? So that's, and you could always flip these functions as a maximization function. Uh, Basically, rather than um, in here, you can, if you put the sum, if you return the sum, I, in a, if you negate the sum, so let's say that you, yes, one way is negating and the other way is you put 1 over the sum. So that can be making it a more of a maximization function. So we can implement and see. I'm not too sure at the moment, but there are ways to make it a maximization function. Okay, so going into the function now, we discussed last week that we want to kind of see how is this working, why is this making sense. Okay, so this much for a number of iterations, it's quite clear, the bounds is quite clear, that you want to generate an initial point between these two bounds. And basically in here, when you are when you are creating a solution, that means making a guess, because this is basically adding random values from this bound multiplied by step size, and that's your candidate. Basically in here, we are not checking if this candidate is going beyond the bound or is it checking. We have to ensure that the candidate should not go beyond the bound. Okay, so you can implement it using a if statement that you should always, whatever guesses you have should be between -5 to 5. Let's say that this for loop here, for example, for now, we guess something and we only accept it in here, basically that guess, if that guess is better, right? So that's what the if statement does, right? So let's, and then there is another statement. In the case if it is not accepted, then we will accept it by a given probability. Okay, so that's basically the two, what the two if statement are doing. If somebody is making a guess and that guess is good, that means it is better than what the current state was, then you obviously will accept that, right? But if that guess is not good, then you would be like, okay, how bad is this guess, right? And am I in a situation, is the algorithm situation that should we be accepting bad guesses, right? That situation is given by the temperature value. Basically, the temperature value is a way to kind of ensure that towards the beginning, you have the probability of accepting poor solutions or bad guesses is high, and then over time that probability becomes lower and lower. So towards the end, towards when the temperature values from high goes lower and lower and lower, and towards the end, basically what happens, this if statement will not be executed much. Okay, so let's say that let's just run this quickly. Okay, let's run this. Okay, we are in session. So currently, what we see here, what it reported so far, um, these things is the y dash. These were all. Where is this being printed? Let's see. Is the y? Okay, so these things are just these things were just done to explain you what a function is and how we should do things. What can we do to functions, right? So things like that. So what I can do is quickly just comment all these so that we just keep the both functions intact. Okay. So okay, we comment this, and let's just comment this one as well. Yeah, so both of these things are commented. We can keep the objective function. This basically implements, it's a vectorized version, right? That means more than one dimension. Okay, so that's this here. So these are all comments now. Okay, so we run this again. So this is what is being said here. So you see this 34. What is this 34? So it's being printed. Things are being printed here. It's like having an old style of a if statement where I is being printed, and well, I'll just make this more simpler. Let's just print it just like that. So you know I is your iteration, right? So simple now to see the print statement. So that's the progress. So that means all the places where the function is checked with the previous version, previous state, that's whatever is your best solution so far. In the current evaluation, whenever it is better, right, it just accepted. So these are the places where it accepted. So in iteration 34 and all the way to 512, okay, that's where it accepted those. And then basically afterwards, what it is doing, it is calculating this whole thing, right? And what is this, right? So let's just print this. So we can just take this whole thing here and we just put it here. So um, the best, we know that that's the best, current best I, and we can put the temperature. What's the temperature? T, okay. Let's also put the temperature T here. This is our own information. And so that's the best temperature. Whatever is the difference between the current and the actual, all this information, okay. So in metropolis, it's basically this it's putting the minus diff divided by T, okay. So that's the temperature. And note that the temperature value actually is reduced over time. Okay. So where is the temperature value? How is it reduced? It's reduced by this statement. Okay. So that's how the temperature value is reduced. It's temp divided by the state plus 1. So now you can see that this whole thing, we have lots of things being printed here. Okay, so what's the first things that's being printed here? It's the I, and that's the best evaluation. And then we have the temperature, and that temperature is being reduced. So you see these values, okay? So these values are being reduced over time. And see, before it used to be at some point of time it was this high, and it began, and that's iteration 12 here, okay? So I'll just put another statement here. This basically means if best, okay, right? And then we will know what's going on. So only when the solution is accepted, then we can say, okay, it's best, right? So what we can do, because it's printing too much, at least we know that idea now, we can just move this print statement in here. So now it is going to be printing only if it accepts the solution with the probability. Okay, so now all these times, we see now less number of iterations. Okay, so less number of prints. The reason is only when your the metropolis, whatever it retains, it is lower than a random number, then you are going to accept the solution. So it's a way to accept weaker solutions, essentially. Let's just say something here. And we could also print how many times we could say, let's say count if so what this does, it will tell us information how many times is the solution that's being accepted actually was a weak one. Count beta is equal, just do a plus 1 right, and we can just print that as well. And count so count weaker, and then we can print the count weaker as well. If there's any comments, you can place that in the chat. Or just say to me directly, right? So now, all the time it's accepting the weaker solution. We are saying if it's accepting the weaker solution, okay? So I think it's better we just put this count weaker here. All right. So, and then we will know how many times that is being done. So the count weaker, it goes to 704. And towards the end, we could just print the count beta and count weaker, okay? So it did around 1000 iterations, and of the 1000 iterations, only 20 times in the 1000 iteration this part was true, but 700 times this part was true. Okay, so if you the, the reason this part is true is because in a function, I have to try to draw, although my drawing skills are really weak here. So if that function looked like, if in the future, because x squared is quite a simple function, it's something like this, right? But if it's something like this and you want to kind of come to the bottom here, right? But if the function is something like this, right? If that's the function, so basically, if you are only accepting the if you are only accepting the best one, what will happen? Like you will come here and then you will say, okay, it's best, and somehow you may accept it best, and then you will basically jump in a local minima. Accepting weaker solutions mean that you are now accepting solutions that are giving bad results. But while you accept these bad result solutions, and so you had a great result here, but then afterwards you are accepting bad results, but then afterwards then you again accept all the these good solutions. So that is how you kind of escaped from the local minima. So these are all called local minimums. Okay, so that's the point of simulated annealing, that at times you need to accept the bad solutions more, and over time, basically towards the end, you will not accept weak solutions anymore. So that's basically the point. Okay, so any questions about this before we move on? As an exercise, what you need to do, if there's a question, you can put it in the chat. I can just see. Okay, as an exercise, sorry, bootcamp, see boots there. You have to see exercise 4 and okay, not exercise 4, the exercise 3, and the exercise 3 was like you need to exercise 3 is you need to look at simulated annealing. And what part is there? That's the optimization part, right? So basically in the exercise 3, you need to not work. So you can do this quite easily now. Multi-dimensional problems. So that part is actually extending it for multi-dimensional problems. That part is actually done here. This objective function. So this is an example of a multi-dimensional objective function, multi-dimensional sphere function. So you need to add more functions here, and basically you may need to change your bounds a bit and a few more things here. So the way that you are generating a new solution, these things should all work for multi-dimensional part. Okay. The point is like, okay, at the beginning, and currently in this algorithm, you have something like your solution space is basically, let's say 3.5 is in your solution space, right? But in a multi-dimensional solution space, you are going to, and you can make it 3.6, 3.4, so you can make different proposals on it, right? And Basically, in a multi-dimensional solution space is like one solution is 3.5, one dimension, another dimension is 3.1, and another dimension is 4.1. So let's say this is a dimension for three-dimensional problem. So when you're making new solutions, ensure that you are using a for loop essentially to add a random noise to this. Okay, the solutions in this case are made by just you're adding a real random number, right? And that's basically that's what's being done here. No? So you just need to add a real random number. And after adding, you should check if your solution space is within the bounds. If it is not within the bounds, then you should again add the random number. So you should keep on adding the random number till it is within the bounds, right? So you need to ensure that your solution is within the bounds. And basically then nothing much will change. These things will all remain the same actually. When you're doing for multi-dimensional, all these things will remain the same. The only thing that changes is when you are updating the solution. Okay. So try that, and then there are you need to try it for Rosenbrock, raster green, ellipsoidal function of 10, 20 dimensions, and then you need to run that many experiments. So that basically, and the details of these functions are given there, and some you can just search for these names, and a Python code will be also online. Basically, these functions are very much similar to what you see, but it's just I mean it will be a similar style, but this line is going to be just a bit different actually. So that's all for this topic. Now we move to another topic, which is the traveling salesman problem. And this is the traveling salesman problem. Example of so the traveling salesman problem, we introduced you to simulated annealing with it. And basically we just need to kind of brainstorm what I try get back to this, brainstorm how it can be implemented, right? And how we can use simulated annealing later to implement this. So this thing is like when you see something like this, essentially this is a graph. Okay, so this is a city number 1, city number 2, number 3, city number 4. So it's just 4 cities. You can think of it as Melbourne, Sydney, Queensland, Perth, something like that, right? And the thing is like going from one city to the other, what's the distance, right? You can think the distance can be kilometers or minutes, whatever, in whatever form. And this is a single objective function, traveling salesman problem. That means you only care of one variable, decision variable, which is a distance. A multi-objective problem is when you want to optimize when you have two things between them, you know. That means the distance and also let's say the time, right? Note that here going in this uh, graph, the other assumption is being made is going from city 4 to city 3 is the same way when you go from city 3 to city 4, meaning that your return journey and going back journey is the same. And that is okay when it is dealing with roads generally, but sometimes between some cities, like you have one route to go and another route to only return, and that time you will have two different distances. Okay, the going distance is different from the returning distance, right? So that's basically the things to be concerned about. And basically when it is a graph, basically that problem is going to be represented as a matrix. So this is called an agency matrix. A graph can be represented as an agency list as well. So if you do a bit of a Google on graph or graph tutorials, you will see on a link on YouTube, there are videos about introduction to graphs, and graphs very important for computer science and mathematics. And It's an important problem for data science because data can be also represented as graphs. And in the area of deep learning neural networks, we also have graph neural networks, graph deep learning, and I'm doing some research in that area as well. So it's when your data is in form of a graph, what is an example when your data is a form of a graph? That is, for example, how social networks are formed. With Twitter, you have multiple users, and all these user profiles are connected to each of the other profiles. So you can think of the network in Facebook, Twitter, LinkedIn as a graph. Okay. And traveling salesman problem, the problem is that you should visit all the cities but only one at once. That means you should not return to a city which is being visited. So that's the major limitation or constraint that you need to enforce in implementing your traveling salesman problem. Okay, so let's look at this. So what does this look like? I mean, it's not formatted very nicely to be displayed. So this is how this graph should look like. And then we have, that all these are 0, 1, 2, 3, 0, 1, 2, 3. That's how it is represented. Okay, so 0, 1, 2, 3. So but here you have cities 1 to 4, but that's like in the real representation. But in the graph representation, we know that your number is from 0 to 3. Okay, because in this language, in Python, our first index starts from 0. If you're doing this with MATLAB, your first index starts from 1. Okay, but in Python it starts from 0. So that's why this 1 actually means 0 in that Python world. So this is 1, this is 0, 1, 2, 3. Okay, so what is the length of 0 to 1 and 1 to 0? That's 10. Okay, so 1, so essentially what we see in that figure there, it is saying that you go from 0 city 1 to, let's say, city 2, the length is 10. Okay, but in the graph world, we know that that's city 0 to city 1, and that's also actually 10, right? So that basically means that the row 0 and column 1, and that's what 10 is. Okay, row 0, column 1. And actually it also means, so you're going from here to there, but then your retaining is also 10, right? So your retaining is also 10. The same root is there. So in here, you see column 1. So then row 2 and column 1 is also 10. You can see. So this is, and the same with others. Another one is 15. That's 1, 2, 3. So city 1 to city 3, that's, it says 15, the length. And city 3 back to city 1 is 15. Okay. So in here, so city 1 to 3, that's what it is saying. City 1 to 3 is 15, right? And that in our graph world here is city 0 to city 2, that's 15. Okay. So where is that implemented? Let's see. So that means city 0, that's row 0, and to city 2, that's 15. And then the way back means that city 2 to city 0 is also 15, right? And in here too, right? Okay, so city 1 to city 0, that means you're returning, that's also 10, right? So this is a very simple example, because in computer science mathematics, we want to kind of develop things using the base example and then expand from there. So this program, at the moment, the example is this, but it can be extended to 1,000 cities or 1,000,000 cities. The idea will be the same. Okay. So this is symmetric, meaning that all the things here, like this 10, 15, 20, that's 10, 15, 20. So you think of placing a mirror in the zeros. And what does this zero mean? It means visiting city one, from city one to city one, the distance is zero. Why is the distance zero? Because you're not going anywhere. You are still at the same city. So all the cities, the within trip going to within the city is assumed to be zero. Okay, let's assume it's like you are at your home and you're visiting your home. So there's zero distance. Okay, so this basically represents the problem, and we want this to we want a very basic naive algorithm. Naive algorithm means the simplest algorithm where we are manually trying to find out what is the best route actually. So that's basically what a naive algorithm in this sense means. So that's how a graph is represented. That's how a traveling salesman is represented. TSP, and that's why it's called naive. Somehow it says 80 here. So what is this function doing? So let's try to understand this function. It takes the graph and then it takes S. What is S? S is 0. Okay. So S is 0. So it takes the X and it says vertex and it just appends the vertex in the beginning. So let's just print out what it appended. Okay. So this could be a root. Like, so what's the example of a root? That's like city 1, 2, 3, right? So that's an example, could be seen as an example of a root. And then here it says that of the vertex, you use get some permutations, right? So what is this permutation? It's basically a built-in function, permutation and combination. So it means all the different types of the different different possible routes essentially. Yeah. So let's just see what it says here. What it returned. Let's see what it returned. So it did not really return anything at the moment. Uh, because it's more of giving some type of a pointer to here, but it's another. So basically we'll need to kind of basically print it just here. Okay, it's kind of a pointer to a list rather than printing there, because then we will be able to see what each of the permutations are of that path. So okay, so basically it gave 1 to 3 to that function permutation, and from there basically it's trying to just see the different combinations of the root. Okay, so for every course, for all the different combinations, what it does, it goes into the current path weight. Basically it will calculate a current path weight. Okay, so how does it calculate the current path weight? It first initializes it to 0, and then it goes to the graph. It places, it has this for loop where the S, which was 0, it is given to K, and basically it accesses the distance from the graph. Okay, so it accesses the distance from the graph, and for every path it will tell what the distance is. Let's see what for that path. Uh, okay, so we can just print the I there and print the pathway. Okay. And distance. We just take this thing out. So that it's just so basically it says if you go from city 1 to 3, that path, then the distance is 95. Okay. How can we ensure that this is correct? So it is saying city 1, 2 to 3. Okay, and the distance is 95. So city 1, 2, 3. So the thing is that because we start the 1 actually is 2. So city 2 to city 3 to city 4. In here, the path is basically these paths are being added. Okay, so that to ensure that we know that we are using the correct things is basically we can just print the current path here as well, so that for all these I and J, K and J, basically the current pathway is being printed. Okay, so that's how we try to understand. So this is a very naive way, meaning that it's not a very efficient way. So we see that start from for city from 0 to 1, the path was 10, and 1 to 2, the 10 was added to the path of whatever was in city 1 to 2. Okay, so this 10 was added to the path of city 1 to 2. So what is the city 1 to 2? That's city 2 to 3. City 2 to 3. So that's 35. So 10 was added to 35 and then it became 45. Okay. Then that 45 was added to whatever was city 2 to 3. And that's actually city 3 to 4. That's 3 to 4. That's 30. So that's how we get, you know, that 75. And then that basically finally then you need to go back to the original city. So this path means basically 1 2 3 and then 0. Okay, then you go back to here. So then I think from here to here, so 75, and then you go to here. So this is 1 to 3. So that means you started from city 2, then you went to city 3, then you went to city 4, then you come to city 1, and that completes your path. So 35 plus 30 plus 20 plus the 10. So because you started, you go all this way. So that is basically 95. Okay. Similarly, there's many of the other combinations and their paths are all being calculated. And at the end, basically, the naive algorithm is very naive, meaning that it computes it just retains the minimum, just retains the minimum path. So that the one with the minimum is what is retained is 80, because 80 is the minimum it found so far found. So that's the minimum. So the reason I wanted you to know this is that it's example of how spatial phenomenon is such as very simple as a salesman problem. The application of troubling salesman problem is in many areas. Okay, it includes from something you use every day to something that you were using a lot, but unfortunately due to COVID, you don't do that. And that is actually flights. When you're booking flights from one area to another, one city to another, then that's more of a multi-objective traveling salesman. It's or it's more of a shortest path problem, because that's actually traveling. That's not a traveling salesman problem, because you're not that problem. You're not going all around the world. So that's called a shortest path problem. It could be seen as a subset of this problem when you're traveling between two, from Australia, you go to Europe and you want to know what path is the one that gives the best route and best fare and things like that. But other examples of traveling salesman, it's used also in circuit design, because all these very small microprocessor chips and motherboards, you see there's all these wires, right, connected, and you see lines of wires connected, and you need to kind of minimize the length of the connection so that it doesn't overheat your microprocessor, which is very complex invention of our civilization. So, okay, so this, the problem here is that this idea is okay for small things, but when your size of the city is, let's say, 100,000 or 200,000 or more than 1,000, and this can take hours to days or something like that. So it's not a very efficient way. So this is because it's the naive approach. Naive doesn't need to be efficient. So the way to do this is that you should use something, you should use simulated annealing to actually solve the traveling salesman problem. And actually, that same simulated annealing, the algorithm is the same. That simulated annealing you can develop, and using object-oriented programming. And you need to kind of have a fitness function or a distance function. Okay, this is not correct entirely, but I took it from somewhere, but I was just trying to think about how this program will be done. And you can take the same graph, and basically you are passing that to my TSP. We are just printing this, whatever the cities are there. So this is at the moment very small. So you need to implement things like uh, sim annealing, in here. Right, and you need to implement a distance function. So basically the distance function, you are giving it any path or a route. Let's say it's a route. You give it a route and you give it the graph. It should be returning, but the graph is already available in the self.graph, so you don't need to pass it. Okay, so that means you're going to play with this self.graph, and it will be very much similar to what it is here actually. So you just need to calculate the distance. Okay, so once your distance is done, then basically your traveling salesman with simulated annealing is quite easy uh, afterwards, So whatever your route is, so route you give, and let's say we are calling that the distance function uh, is equals to distance. There any comments, please place it. I'm just trying to rush a bit because I want this to. So let's say we covered. Uh, so let's say that we have a route example, So let's say the route is 1, 2, 3, and 0. So that completes. So we pass this route, and it should just print that route. So, and, and then the rest of the simulated annealing function will go there. But the basic thing is what is happening here is that we are calculating the root, and to calculate the root, we need to access the graph. Okay, so I don't. So for the range, it should be whatever is the size of the root, length of the root. So we want to kind of go into, take that root and access the items from here to actually get the items from the root and then put it in the city, basically. So it's like your current city and your next city. So let's say you have current city, then you will do a root. Let's say current. We're making things simple, okay? So that's from your root, you're taking the current, and then you are saying, okay, that's your next city. Then again, from the root, you are taking the next. So if your root was 1230, so you took 1 as the current, and that, right? So now let's just see what happens. Okay, fine. We can print the distance. We can print the current, next, and distance. Okay, so can see that I don't want to make assumptions. That's how I program. Uh, I will usually, so you develop a function by function, you test if that function is working, you make sure the function is working, and then that's how, then you move to the next function. But to make sure the function is working, you need to print states of that function. So currently we just had that the city being printed. Then we have my, and this is all, let's say, the main. Okay? So that's one way actually, and there is an error. This is one way, and it's saying that there's some problem somewhere. I don't know what that is actually. Let's see. So it says the current, there's some problem with the way it's a list, or and somehow it's not accessing things well. I thought I gave it a list. So we will move on to other issue, go to other problems. This is something that I leave it to you to fix yourself. Another thing is that that's one. This is one way, but here actually another way, you'll see a lot of online implementations for simulated annealing and traveling salesman problem. They usually don't do this distance idea this way. There's like, because the online implementations, they try to visualize how the cities are looking. So every city has a x and a y coordinate, okay, and then the path is calculated by going through these x and y coordinates and computing a Euclidean distance, so the sum of the Euclidean distances between points, so the distance between all these points in spatial area. So that's what the traveling salesman visualizations are implementing. But in the real life situation, it won't be that way, because it's not that all the links to all the different points are going to be straight. Okay, so that's a problem. So this way, the way that we are representing in a graph, that kind of assumes that, let's say you are using Google Maps or something and extracting the city distances. You have some kind of an interface, and then you are using that to implement it. Okay, so there's a kind of a kind of I had this solution from the past, not very efficient. Okay, this is not really traveling salesman. It was just showing an example of a simulated annealing, and the problem is the Rosenbrock function is implemented that way, and this is a Scherfeld's problem, and Schroeder problem there. So this is, you could see this as a solution to the previous exercise, and the generate a new solution function basically is just adding things to that to here, right, to the place which is fine, which is not really this exercise solution. Moving on to this exercise, TSP with simulated annealing, you have to do all these things, implement it for a small number of cities and go larger, and then you compare with your, can you do it for very large number of cities, and you then later, once this is working, then you can think of implementation. What I'm saying is, in the online implementation that you should see the visuals, this is always a straight, you see straight points, and then they usually just take the equilibrium distance basically, and that's basically there's a link there that is talking about that, and there's also a potential solution, it is saying here, which I cannot really open right now. I can probably open that with okay, let's just leave it. You can open that and check. Okay, there's a good visualization. So this is all the troubling regarding troubling salesman problem. Just one thing, if you are doing it the other way, it will be basically, instead of your root, it will be, because your root now is, it can be like this, so it's basically, you should give it the coordinates, root by coordinates. So like, you could be in your coordinates of the root, you can always say like 1 2, it will be basically become these values that you are going to give are coordinates, and it will be generally the double the size of the root, right? Because each point here can be represented by a coordinate with a x and a y value. So when you do encode, when you decode these, uh, it should have x and a y value that is decoded, and that is basically taken, and you do equilibrium distance kind of a thing. Anyway, so I hope that this kind of gives you some hints. So that's this is that function, and there will be another function, of course, which will be generate a root. Okay, ensure that in this function you do things, ensure that the root is correct, meaning one city can be visited only once. Okay, which means this is correct, this is a correct root. For example, this is a correct root, but this route is not correct. So um, this route is not correct. Why you are visiting your city to again. So that's not a correct route. Okay, so let me just push all this quickly so we can pull and try this. So this is all the hints I can give. Essentially, in your simulated annealing function, you are going to calculate the distance of a route. You are basically going to get this whole thing, and you are going to translate this into Python here. But in here, the energy, what the energy is essentially your distance. The S mu is your new route, and that's it basically. You're just dealing with the distance and route. You keep on updating your route. You need to generate this generated this neighborhood candidate. This means this part basically means you need to call this generate route function. Okay, yeah, right. So we'll take a 2 minutes break, and then we'll continue with the next two lessons. Okay, we can continue now. Any comments or questions, please mention it in the chat. Okay, so next we will just now we are kind of slightly diverting. So this whole traveling salesman problem, that's an example, and the previous optimization problem, these are example optimization problems. The previous one was which was function optimization. That falls in research area of global optimization and simulated annealing and evolutionary algorithms. A lot of people do their PhD and related research in that area. And traveling salesman problem is more of combinatorial optimization or discrete parameter optimization. So that's how the previous one was continuous parameter, and then now discrete parameter optimization. And these are all their own areas, and there's a lot of resources out there. The reason we are using this as a programming exercise is just to give you an overview at how these very simple while loops, for loops, if and else are being used in big problems. Okay, so next comes this is more of an introduction to data science or data analytics, an introduction to machine learning. And that is where, first thing first, you need to learn to process data when you are looking at machine learning algorithms. I don't have time to really motivate why we should do machine learning, why should we be interested in data science. I just I think a lot of you who are attending this boot camp, you're already motivated, right? And I know that some of you are doing your research, postgraduate research, and some of you are doing some other forms of academic research, and optimization or data science are central to all these things. So from now till Wednesday, we are now going to look more into the very basics of data science. Okay. So in machine learning, data science, data mining, there are data sets out there that are used to actually test algorithms, and the goal of these algorithms are actually to classify things or predict things. And one such example is the iris dataset. Okay, so iris dataset, actually it's quite a well-known data set, and there's actually even a Wikipedia article about this iris dataset. So it's a flower, and it's a multivariate data set. Multivariate meaning there's more than one features, and in this case there are 4 features, and the features are sepal length, sepal width, petal length, and petal width. And this is the iris flower. Coincidentally, yesterday I was when I had to change my body wash in the shower, and then I was just reading what's in the body wash. It said it has iris flower extract. I was like, okay, what a coincidence. Tomorrow I'm going to go over this iris flower, and there was a photo of iris flower in the body wash. So body wash bottle. Yeah, so that's interesting. So there are these 3 different types of iris flowers that we need to recognize or classify, right? So machine learning algorithms are basically used to classify things, and it's one of the very basic statistical and machine learning algorithm is called a logistic regression, and another one is a linear regression. So first, we need to understand this data set, and linear regression and logistic regression can be used to classify or predict things, okay? Predict the future, like what will be the temperature at this time today, tomorrow, looking at all the past temperatures of previous years, something like that. So prediction is important. Classification is important. We do classification, prediction every day in our lives. Okay, we have intuitively we do keep on calculating things that are going to happen. We plan things, and we do follow weather predictions, and we sometimes predict things ourselves. Like, okay, this is an app is saying that it will rain in the next hour. My app, phone app is saying that's what I have. And should I take an umbrella to the park or to my office or not? And then when I look outside, I'm like, oh, there are no clouds. It doesn't seem it will rain in the next couple of hours. So sometimes we fuse data and then we make our own predictions based on our own information. So that's fusing data from multiple sources. So there's the area of data science, machine learning is very vast and very interesting. So that's why some of you are quite interested in doing this bootcamp, I'm sure. So there are different strategies that can be done to do any of these predictions and classification uh, tasks, right? And actually, there are machine learning data sets known as sklearn, which is and basically you do not have to download the original data, but you can just basically use the data from sklearn library. The library has downloaded and processed the data for you. But we want to see where the actual data is. So in the actual data is in this link where most of the other machine learning data sets are. So this is the actual data set and this is the data folder. And in there, basically it says iris.data, iris.names, and you can download them, save it in your computer. And basically, I think if you're using Windows, this may not really open, but if you're using Linux, this opens. Probably it may open in Node++. You can convert this into, XLS, CSV. You can convert it into CSV. So here, basically, we see iris. We see the four features, which are one, sepal length, sepal width, petal length, petal width. Okay, do not trust me. I'm just guessing this for the the order of the features, but it is one of those. There, these combinations. And then there are these three different types of iris flower data set. Usually in machine learning data science, what do? You have a model, right? And then you basically read this data, and then you kind of, from this data set, you create two sets. One is called a training data set and one is called a test data set. Okay. You can create those two sets, and usually they are created randomly, or at times you basically pick the first of 60 or 70%, you call it training data, and the other you leave it as test data. But in this one you cannot do it, because you should ensure that the three classes, which means iris virginica, it is also part of the training data. So if you just pick from here and say, okay, I'm taking the first 60% as training data, then you don't have the last class, meaning that your model will be trained by only knowing two classes, and you want it to test, and it tests only two classes, and that's not a fair training model, fair model or efficient model. So that's why people usually will be taking, okay, I'll take like the first 50% from one class, another first 50% from the other class, another 50% from the other class, or 60%, that's 60%. In that way, or you just randomly pick it. So random number generation picks different ones, and As soon as you get 60%, you say, okay, this is the training data. So that's how you create a training and test data set. This is an example of a very nicely done data, meaning that you do not have missing values here. So sometimes your data will have missing values, like here there's nothing, you know, or sometimes in this data set they will just put something like a question mark that represents a missing value, and then you're trying to read this data using numpy will give an error. So this is, and this data set you can't read using numpy load text or gen from text, because the thing is this data has both numbers and text. When there's both numbers and text, and numpy can't read. Okay, so that is when you need to kind of do some processing, and the processing can be either manual or automated, right? The automated processing, there's another library called pandas, which is similar to numpy, but you can use it to read this data set and run some code there, and it will automatically process. You can think about the missing values. Sometimes when you have missing values, what do you do? Sometimes you can take the entire row or out, that's cleaning data, or sometimes you can compute the average of the column and put that average in the place of the missing value, right? So these are some strategies usually done. And okay, so I mean, if your missing value is from iris sentosa, let's say there's a missing value here, you should not take the average, and that missing value is, let's say, petal length. You should not take the average of all the three. Okay, your missing value should be only of that particular class. Okay, we'll take the average of the rest of the values in petal length, the rest of the rows, and let's say this was missing, then you will fill that with the average. This was missing, let's assume, then you fill that with the average. But in here, basically, I'm just trying to not use pandas. So these are very basic data sets, and there are not many classes. So what do? You can do a find and replace, you know. So you can just do a find and replace. So everywhere you have iris sentosa, you just say 0. Everywhere you have iris versicolor, you say 1, and you say virginica, you say 2. So that means those are the 3 classes. Okay, so that's one way of data processing, and that's, after doing that, you can do that, or you could represent them as binary, you know, because the number, so so you have this 1 and 1, basically that represents number 3 and 2, and then you can have a 1 or a 0, something like that. So you can use that combination as well. Or you could have a one hot encoding. A one hot encoding is basically, let's say you want to represent number three classes, then it will be like 0, 0, 1. So that means this is class 1, then that's a 0, 1, 0. That's class 2, and 0, sorry, 1, 0, 0. So that's class 3. So that means in the place, all the places where iris the first class, you have 3 values basically to represent, right? So this is one hot encoding, and this is the way that you should generally use with the neural networks and machine learning methods. It's quite especially deep learning methods. So there are many ways to do it. So what we are doing first is we are just learning how to read this data. Okay, so Python, and then process the data. So let's assume that the basic processing has been done. So that's the data processing code here, and we are reading the data, and gen from text, because we can read the data because it's already in a CSV file. We're seeing this is the delimiter, what separates the values, and this is a Python function. That's basically the import and numpy star that kind of ensures that this function is imported. And so the things here are very important. What this means, when this does, it basically imports that whole data set. Okay. Iris binary encoding.csv from the data folder. So there's a data folder there, and that's the one. This is imported, that whole thing, right? And then now we need to basically, let's say, generate processing, and we need to kind of check where are all our features, right? So basically, this is the code where we say, okay, all the rows, basically all the rows, we select row column 0, column 1, column 2. So that we have 4 features. So the fourth one, of course, doesn't get selected. This means that it's selecting which are 0, 1, 2. Okay. So that basically plays this input X, right? And here it says this is the target, but actually this is not the right way. -1 you could do when you are just selecting the last one, but in this case we need to basically go from 4 and 6 basically. So 4 and 5 are going to be now selected. So that means in the data set, the fourth column and the fifth column are being selected. But to do that, you need to say 4 to 4 and to 6 basically. Okay. And you need to put a comma there just as the last one, and that will select that data, that much columns. And then basically here, what is happening is, let's run this. So basically, you can see the print. Uh, Statement. We have now we are generating a training set and a test set, and basically in this one, which is not really correct in the sense that I was telling you before, it is just taking the leaving the rest, the last 20 and everything in front, it is taking as a train set, and then the other it's making a test set, right? So from so that -20 means that from the end leave the 20 and everything becomes the train set. So this is not a very efficient way, but I'm just showing an example of how this can be done. But what you can do is implement a function so that the training and test set are randomly picked. Okay, so you need to go through the data and randomly pick and generate a training set and a test set. So you can write a function that does that. So that's one way for you to test your skills so far. You'll be using a for loop. You will be going each data set and then just generate a random number. Either it's a 0, then you can say, okay, this belongs in the training set. So you go from here. So you take this, right? Let's say, and then you generate a random number. If that random number, you know, could be either 0 or 1, that type of random number. Or you could be like generating a random number if the random number is in the range of 0 to 1, and if that random number is less than 0.5, then you pick this and put it in the training set. Greater than 0.5, then you'll put this and put it in the test set. So you'll do that same thing for all of them, right? And in that way, basically what happens is your training and test set is generated randomly, but you do not, the size you are not determining upfront. So you need to, if you're saying that you want 60% of the data to be in the training set, that's when you need to think about how to do that. Okay. So you need to keep on counting and keep on picking. So sometimes your training and test set could have repetitions in order to really ensure that that 60% is there, or at times it does not need to have repetitions, and that all depends on how you implement it. So there are the functions or out there that does it for you, and by Wednesday or in the next lesson, we will see how that is done. But anyways, whatever is being read, the training test set, although it's not correct, but we have divided the data, right? We have divided the data. So what you can do, then you can generate, some stats, use some statistical tools like NP mean to find what is the mean of each of the features, right? So in here, basically, when you say NP mean axis is equal to 0, what it does, it goes to each of those features in the train set, and it gives the mean, right? And then when you say NP mean axis is equal to 0, uh, NP STD axis is equal, then it gives the standard deviation. So that's how the mean and standard deviation works for like a table of data, right? If you change this axis to 1, basically, what will happen? You will have it the other way, meaning you will have a large set. Why? So this is like, so the previous one was the axis is like, so you're getting the mean along the columns, but this is the mean along the rows. Actually, this is the mean along the rows. Okay, so that's where it means that axis is equal to 1. But that's not usually useful information, the mean across the rows. And then you can also, the rows and the columns, you can make histograms. And another thing is you can make a covariance matrix, and covariance matrix basically gives you an indication of how correlated are those features, right? And then you can print the covariance matrix, and you can also um, and that's what's being done here. The covariance matrix being printed, and you need to just check if this covariance matrix is looking at covariance across the rows, or the covariance, this means covariance of the instances which are given in rows, or covariance amongst the features. It seems that because the size is quite large, it seems this is by default giving covariance of the rows. If we do a dot t, it may just give the covariance of the features. Yes, now it is giving the covariance of the features. The dot t basically, rotates your data. So now we see the covariance of the features, and the covariance matrix, basically you get the standard deviation in the covariance matrix, or variance in the covariance matrix. Please check that. So read about the covariance matrix, and then print it out like this, and then basically you can even save this as a heat map. Okay, and all these things basically that I've been telling you, that is actually, I think, given as your exercise part 2, and you can do that for the other data sets, right? So now let's move into the next topic, which is gradient descent. And this topic is actually, I placed some lecture notes there, which I have written for my other courses. And from there, I've just extracted some basics so that we can see what these are actually. So, so this is an example of a Rosenbrock function that I was telling you, and that's the Rosenbrock function. Okay, now we see the function. You can use this, and this is actually a 2-dimensional Rosenbrock function, which means you have x1 and x2, and this is like looking at the Rosenbrock function from the sky or plan view. Okay, and basically we want to go into the minimal part of that Rosenbrock function. And this is another example of a function which has two variables. and so you could think of y as the x2, so it's like x1 and x2, okay? Or in the other way, you can think of it as xy, and the output is z, right? And in this function, basically, we want to find what is the minimum, right? So you can do simulated annealing and find the minimum as we discussed earlier, or you could use something called gradient descent. And what is gradient descent? Gradient descent is a similar algorithm than compared to simulated annealing, but the other feature of it is that it is using gradients. So it's more of an iterative approach. Simulated annealing is known as a global optimization function, which is stochastic or meta heuristic, whereas gradient descent also has some stochastic, and this it's not a meta heuristic, but it is a heuristic that uses gradients. Okay, so what is a gradient? Gradients are basically the derivatives, and basically that can be useful. The gradients can be useful to tell you which direction to go on so that you can find the minimum point better or faster, right? And so those gradients basically are used to do an update of your parameters, right? And in the simulated annealing case, you were updating the parameters heuristically. You're just making a random guess and just checking that the constraints are satisfied. But in here, your parameter updates are going to be done not heuristically, but using the gradients. Okay, so let's say this was your function, right? We just dealing with a one-dimensional problem at the moment, just an x. So the function is x to the power 4, 3x cubed plus 2. So that's your function. Then its derivative is the very basic derivation here. The 4 will go in front, and the power you do -1, so that becomes 3. And then 3 times 3 is 9, so the 9 is there. And then x, and then minus the 3 minus 1, that becomes 2. And there's that constant basically is taken out as 0. Okay, so then basically we need to solve um, this basically, right? So the thing is that this example you could just do it manually, but the reason is we are just using this as a very basic example to show how gradient descent works. Okay, so we know that this is actually the solution, the x that you should have, the value is 9/4, but we want the gradient descent algorithm to find the solution. So we can just implement this. Okay, and I have done this. Let's go into the code, and the code is actually here. And move from the data processing. Quickly run this code. So that was the problem. So you can see that so that was the problem. And gradient descent can be implemented using a while loop or for loop. So for gradient descent, just similar to simulated annealing, we need to give it some termination condition. In simulated annealing, the termination condition is that could be that when your temperature reaches 0, you keep on doing this, right? Till your temperature reaches 0, or till you have a maximum iterations of 1000, right? And in here, we also need to give it a maximum iteration. There's no concept of temperature here, okay? So similar to simulated annealing, you have a current and a next, right? And basically, we have a function, the 4x cubed is here, right? And 9x squared, that's the derivative of the actual function, right? And basically in the derivative, we will pass the current value of x, right? Multiplied by the gamma, which is user defined like a 0.01. And in the linear regression or in neural networks, this gamma is called learning rate in the area of neural networks. And whatever is the current multiplied by gamma multiplied by the gradient. So that basically is a gradient. Okay. So that basically will give you your new value of x. So this part basically in the simulated annealing, it's you're just generating adding a random noise, small random noise to the current to create a next. But in here we are looking at the gradient and then using that gradient to calculate the x. Where we first take the value of current when we pass it to whatever is our derivative, and from the derivative we get the gradient and then we update. And we keep on doing this till we either reach a precision, meaning that the values between the next and the step, which is the step we something that is user defined. Hold on. Okay, in here the step is like the next minus the current, right? So this means that we are taking steps in moving through that valley, that hills and mountains and valleys, that region that we just showed, right? The 3D view. And we are moving, that's called the step, right? A time comes when the step becomes very small. That means we are not moving anymore. And so that's why we give it a precision, user defined, and that's a way to, let's say, stop in case we are not moving anymore. So that means you have converged to a solution. So that's you stop that way, or you stop when your function reaches the maximum. Okay, so you started here when you the initial value that was given. So we start, and basically this is just the function is here, and this is, you can think of this as the main, something like that. So in the main you are calling that function, right? And in the main you just have a for loop, and these are your global variables on top there that's defined by the user. And actually in here you start, so you need to give it a initial position, and in here the x that we started is at 0 at 6. Okay, so 6. So we take that x, and then we will be calculating a gradient, things like that. And basically we print I, we print the next x, and the next x that is printed is there. And basically whatever is the gradient, we print that gradient value there. And that's what you can see. So these values, the one in the middle, they are basically the values where you are exploring. Okay, and the values here you can see these are the gradients. Over time the gradients become smaller and smaller as well, right? So in the beginning the gradients were very large. We were taking it's moving all around different directions, and basically you see that it says the minimum is 2.24 something something. This is close to approximately 9/4. Okay, so that's how gradient descent is used to solve this problem. So this is gradient descent working on some normal simple optimization problems. Next, we are going to now look at how gradient descent can be used in a linear regression model for a data science problem. Okay, and that is here. So any questions or comments, please put it in the chat. Okay, nothing so far, so I'll just carry on. So linear regression basically is defined as this function. Here we will learn about the mathematics behind the gradient descent and linear regression, and this is our linear regression model. So actually a linear regression model is very simply given by the equation of a straight line, okay, which is mx plus b, right? And in the diagram, I mean, this m and x and b, you can always call these variable names as you like, right? So in here is w0 and w1 and x. So that means the m is w1 in this diagram. So we have this, and what are these green points? These green points are your data points, And basically we want to see how well a line fits those data points, right? So, and what is this? That's basically the gradient. The M is the gradient and the B is so your W1 is the gradient, and what is your B? B is the y-intercept. So this is your B, the y-intercept. And basically the W1 is the slope. So the slope is given by change of X and change of X and change of Y. That's your slope, okay? So, and that's the function. So this is basically a linear regression model. How do we program this? Good. We program this, then we will know better. So let's assume that we have a data set, right? We have a data set X, Y. So this is our data set, X values and Y values. And you can just imagine that this is being printed, right? So you can just do a scatter plot and print these values. So you can think of X as and Y coordinates, something like that. And that's basically it's a sum of squared error. So that's an error function. So in this linear regression model, error function is very important, right? The error function basically decides how well you are fitting this line to this data, the green points, okay? So that's what the error function does. So that error function, replacing in the t in that error function is your basically your target, and the O is the observed, right? So we can update that equation. The O or the observed is basically your Y, okay? The Y values here. So all these Y values, all these 14, these Y values here, 31, 68, and all those things, they are basically a vector here, okay? And 1 over n, in this case, the n is what? Take the 1 out, so 13, right? And basically for each of those, you are going to compute the mx plus b. And your x, your m and b, these are two variables, basically. They are the things that needs to be optimized, right? So your m and b are the variables that need to optimize. Your gradient descent algorithm will find the best value of m and b so that you fit this data. Okay, so that's the goal of your gradient descent algorithm. So what happens is because this is your target, we are just replace that by your model. Okay, so that's the model is mx plus b, and the whole thing is squared, and so it's basically the same equation. It's just that the t is replaced by the model and y is replaced by the o, right? So basically, and that is implemented very simply with this uh, function here. It's taking the b, the m, and the points, and basically for each point we take out from the points. The points is your data, okay? So this is basically your data. Let's say you read the data and called it points, and then you pass initial value for b and m to this function, and this function goes to your data, takes a value x, y for every point in the data. That means it starts from here, it takes this value out and this value out, right? And then it computes this, the total error, which is so that it implements this function, right? So this is how the error is implemented. This whole function is implemented. And this inside part is this y minus mx plus b squared. Okay. So 2 asterisk, that means basically you rising to the power. And this whole thing is you keep on adding it. So for each of these values here, you calculate an error value, error value, error value, error value, error value, right? All of these have their own error values. They are all being added to the total error. So that's what that does. The next, we need to kind of find what is the derivative of m, what is the derivative of b. Okay, so and why we do that, so that we get the gradient and so that we can update them based by the error. Okay, so that's how we update those two things, because we want the gradient of b and the gradient of m so that we can calculate the new value of b and new value of x. So that's how now the gradient descent is working. So the past gradient descent algorithm that we had for that simple function, that was not dealing with data. But in this one, we have data and we have a function. And that basically, our function is this. You can think of this as a fitness function, but this function is depending on the data because there's a lot of points in y, right? So you can think of that as that way. And then basically we get the gradients, because the gradient of m and b, you need to basically find the derivative with respect to this function, right? So if you differentiate this, basically this, the 2 will become 1, okay? And 2 will go in front, right? So that's why 2n, and the sum remains as it is, right? And then you have xi y minus b, that's the same thing there, and which is the model remains the same. And basically that's the derivative with respect to m, and that's the derivative with respect to b. And in the b one, in the only difference is that you do not have any value, where both of them are very similar. Y-I-M-X plus b, the other top one is y-I-x plus b, but the top one is multiplied by the x, which is it's being multiplied by the input, whereas the second one is just not multiplied by anything. Why? Because in here with the derivation, you are doing this partial derivatives with taking in with respect to the other variable, and in there when you are doing that, you kind of assume that the other variable is a constant, something like that, right? So have a read of derivatives, basics of derivatives and partial derivatives. And on Wednesday, we are going to go over the equations again, okay? So don't worry too much. So I just wanted you to see the code, and that's what the code looks like. And then basically we have a gradient descent runner, which basically calls the step gradient code for X number of iterations. So the step gradient is basically calling using the points, using the learning rate, which is given by the user, and using a B current and M current, which is the beginning, which is defined by the user. Okay, and then you have a function called a run, and the run is calling all of these things. And so you have the points that were there. If you plot it, it will be like this. Okay, and when you over time it is running, then it will basically this weird thing, this is the gradient, the line should be coming in here. Okay, so you want to see the animation for that, then just click on this and you will see that. And then there's the line slope and the intercept, that is also the m and the b values for different iterations are being updated, right? So let's just quickly run the code. So we have a linear regression from stretch, right? And then it says running, and then that's the value of B and M it gave. And it gave an error of that, okay? After 1000 iterations. So let's just open that. We have some time. Let's spend another 5 minutes on this to really understand this. I don't know why this thing is not really showing up. Okay, here it is. So all those functions you already saw, and this is where it's calling them. Let's try to understand what are these some of these values that we get over time. Okay, so for number of iteration, print B and M, and we should also be able to print this. What is the error given that value for B and M? Okay, so we just call that function, which takes the B and M and the points. Let's just make it. Let's just put this here. Okay. So and then one other thing, let's put. We want to know where we are. So okay, so you see there, these things are being printed. But for a long time, the error is just around 112. And for a long time, your points are not really changing that much. Okay. It's a very simple problem. But in the beginning, you see, in the beginning, the error was very large, 1400, around 500, around 200, and very fast with gradient descent. In around 9 or 10 steps, actually, it almost converged to a solution. Okay? You don't really need 1000 points. I think just 100 iterations is okay, because you don't really, you won't produce. See, even with 1000, the error was around 112. With 100, it's around 112. And with 52, it will be, I mean, with 10 even, it's around that, okay? So that basically means that your gradient descent has actually this whole thing, basically you will see a line like this. You can imagine that line like that. How? Because your y-intercept which you get. So what are the things we are printing? The B and the M. So B is your y-intercept, it's close to 0, and M is 1.47. So in the figure, basically it should be close to 0, the y-intercept, and that's basically one way to show that it's working. Okay, so this can be used to apply to, for example, the iris classification problem. And in the iris classification problem, basically, first thing is that we need to do is it could be that okay, this linear regression, we can just apply it for two things. Okay, so one is classification, another is regression. Okay, so by default, linear regression is used for regression problems. So this is another example where this is the data, and this is we're trying to fit that, and there's another relationship there. And basically, we can see, we can use linear regression to find if two variables are correlated. And basically, if two variables are correlated, they will have a correlation coefficient, which is called the R score. And R score is a way to kind of check if two variables are correlated. And a negative one will say this a negative linear relationship. A zero means no relationship, and a positive one means a positive linear relationship. And the values, positive values means. So that's these things you can read it up, right? So that's how R squared score is computed, and that's the equation for the R score. So what it means is, why are we using a linear regression? And what does this mean have to do with the R score? Basically, that data that you are generating, the data that you have, basically when a linear regression model fits, basically for every point, every X value in this data, we have the actual data, which is this data, and then we have the data that is represented by a linear model. Okay, so now you have two values of two forms of your data, and that we're going here as well in the beginning. So you have your green ones are your actual data, and the line here that represents the data that is represented by your linear model. So after your linear model has been trained, that means after you've found the value for M and B, you can use that model to generate data, and that data is being compared to the actual data, and you can find a R score that those two, right, things. So basically, you can use it to find how two variables are related, and so on. And you can also use it to model some simple things. For example, house price in a city and things like that. So all these things we are going to cover more in the Wednesday class. So in Wednesday, we'll go briefly go again with linear regression. We are going to see how linear regression can be implemented from scratch. We saw already, and how we can use inbuilt functions from a machine learning library called scikit-learn. And then we are going to go and see a logistic regression, which is very similar to linear regression, but it's more useful for classification problems. And then we are going to then move on to very basics of feed-forward neural networks. And that's where how we are going to end this our programming bootcamp. And as an exercise about the linear regression, basically, we have exercise 4, and the part 3 is kind of an exercise to expand your understanding about linear regression by using computing an R score on the iris power data set. So we can discuss this further again on Wednesday. And there will be another part 4 and part 5 in this exercise series. And that basically ends the bootcamp. And Wednesday, I hope to see more people, and we'll try to make it more interactive. Thank you so much. If there are any questions or comments, do let me know. Okay, I'll just stop recording then. Thank you so much.